Again, hello everyone. Thank you for the introduction. My name is Todo from the University of Tokyo. Today I want to talk about quantum AI infrastructure through integration of quantum computers and HPC. This is the title of my presentation. In my talk today, why quantum AI, quantum computer, when we think about them, why do we have to consider HPC? And what are some of the challenges that we face, and also a project that we are involved in. So those are the topics. So currently, AI is often talked about, but there are problems. One of them is scalability. AI that is used today, or machine learning, in order to increase accuracy, we have to have gigantic amounts of data. And to improve accuracy, we have to have complex model. So in this phase of training, enormous amounts of resources, including electricity and computation resources, will be required. On the other hand, high-quality data is limited. In the near future, we may have little access to that high-quality data. On the other hand, HPC or GPG that are supporting current AI technologies are now facing the limitation of miniaturization. Now, if you look at quantum AI, there are several possibilities going forward. In recent years, we have seen quantum devices, quantum bits, and we have better technologies to control them. Also, as I will discuss later, small amounts of data or small amounts of parameters can result in higher quality response in quantum computing compared to classic computing. And the simulations that are difficult with classic computing can be applied to quantum computing to get better results. For example, this is quantum machine learning possibility. On your left-hand side, we have reservoir calculation. Professor Yamamoto in the beginning talked about this. We use reservoir to come up with this final part to be fed into machine learning. This is very similar to quantum computation. Well, partially, it is not used for training. This is a complex system. And also combining classic layers, we will be able to achieve a very high accuracy results of machine learning. On the right-hand side, you would see the event classification example. High energy physics experimentation is the example here. There are multiple events that you have to look for the events that you need to focus on. But please note that we have the number of events that are used for training on the horizontal axis, and we have accuracy on the vertical axis. Orange and blue are the results of machine learning, conventional machine learning. Of course, if you increase the number of events, you see better result. Now, the quantum machine learning result is indicated by green lines. What is characteristic is you only have 100 events, but stable accuracy has been achieved. This is a possibility of quantum machine learning. With regard to quantum simulation, there will be a quantum variational simulation and also quantum dynamics simulation are some of the examples that we have today. For small molecules have been simulated with quantum computing, but today we also have periodic simulation is available. So this red line is the accurate result. And as you can see, the quantum computing comes up with similar results. and non-linear. If you look at the base states, you can actually evolve that over time, and coefficient will also evolve over a time series, and that can be now traced with this framework. Another example that I like to cite here is quantum optimization. What I'd like to introduce here is, as was already discussed 2 presentations before, there is a talk on optimization, but I'd like to focus here is the cost function, which is not known, or it takes a lot of computing resources or computing cost to come up with the answer. For those problems, for example, the condensed matter physics is a typical problem. Once material structure is given, property can be predicted easily. On the other hand, from property to structure, in this reverse process, it's very difficult. So what we are thinking is to design a material, for example. When there is a material that we want to design, we want to optimize the structure of the material. When a form is given, the condensed matter can be known with large-scale simulation, but it cannot be exhaustive. So what you have to do is to look at only part of the materials to analyze. And what we want to do is to try to extrapolate that with machine learning model. And quantum annealers can actually use it for optimization. Starting there, we will be able to continue on with prediction. And that's where we would apply large-scale simulation. If you repeat this process, for example, GHG emission reduction, we can possibly release energy into a far space. So this is often referred to as black box optimization. That's also possible. On the right-hand side, you see nano-level heat engine problem. There is a potential there. By changing the former potential, heat can be absorbed from the outside. And this exchange with or interaction with the outside can be optimized. In a very small nano level, heat engine efficiency can be improved compared to the conventional model. So now, regarding HPC, we believe HPC is going to play an important role in those problems. In what context? Quantum computers and HPC can form a hybrid. Fugaku, a supercomputer, we have supercomputer in Japan, and high performance GPGs are available. FPGA is also accessible. And quantum computer devices are already in the market. So we have multiple tools. What we want to do is to have an environment where we can use all of these seamlessly. So HPC, where is it going to become very important? There will be many important applications. For example, quantum circuit simulation. HPC is already utilized. Algorithm is developed, and that evaluation can be done with it. What is the limitation of quantum computing? Where we have to apply quantum computing. So I think it is necessary in that sense to have quantum circuit simulation. Another example is quantum error correction or error mitigation. Error correction, error mitigation, suppression. We tend to use external resources, meaning that we have to have high performance computers. If we are to use quantum computing efficiently, we have to have compiling or quantum circuit optimization need to be done in a preparatory process. And this is where we can use HPC for this optimization. Or eventually in the future, we might want to use a quantum computer for this preparation. But today, there is a possibility of utilizing HPC there. As I explained yesterday, this is related to I/O as well. Using a quantum computer to do calculation with quantum computer, the bottleneck is the data that is extracted from external environment. So you have to prepare the initial quantum state. This is also where HPC can be used for that preparation, and then followed by the use of quantum computers. In quantum computers, there are multiple types of quantum computers, devices to measure quantums as well. How can we combine or connect them together? For this connection, we believe that HPC is necessary. So those are the things that we need to give consideration to. And this is the motivation for us. In 2022, we started the project named SQAI. Tokyo University, Keio University, Weekend, OIST, Chicago University, Kawasaki City as a municipal government, and we have 30 private companies of different industries participating in this project. Our targets are, as you can see, the final target, as I have explained, is to create sustainable AI. AI itself needs to be sustainable. And we have specific target sets. Quantum machine learning methods development is one, and we want to develop the method for quantum simulation. And to make it possible, quantum HPC hybrid infrastructure needs to be established. And that will be the sub-target. And we have 5 topics to achieve that. 1, 2, and 5 are related to target number 2. And this topic 4 has to do with optimization. The quantum HPC hybrid, in order to use that, we need to have multiple optimization technologies in use. And also quantum embedding is another topic that we need to focus on. What does it do? I think this is a very critical issue. So quantum HPC hybrid, in order to realize this hybrid environment, a challenge or the core questions that we need to ask would be, first of all, the classical computers can generate a lot of information. It can process a huge amount of information. How can we embed that information into the quantum computers? On the other hand, how can we embed the information from quantum computing to classical computers? Embedding, in this case, is really transferring information. And there are multiple challenges. So our idea is to come up with a new data structure such as tensor networks and Boltzmann machine. Some of the new data structures that emerge in other sectors can possibly be utilized here. So tensor network, what is a tensor network representation? Vectors and also matrix, these can be generalized into tensor networks. When you have 2 numbers, you have a matrix. When you have many more numbers, you get tensors. All of these circles here are tensors. So in order to represent quantum state, you have this idea in the area of condensed matter physics. Exponential coefficient can be held by wave function in a very small group of small tensors. You can express that in this group by decomposing in this way. With classical computing, we have to have exponential numbers, but then we can actually express that, represent that in a very small number of bits. And strict representation is possible with tensor networks in many problems. And extracting information, which is often referred to as renormalization in the physics world, extracting most important information is also possible. Recently, tensor network is now being applied to other technologies like machine learning. Basically, matrix, for example, it can be replaced with a tensor network. One example is in the area of deep neural network, machine learning, deep learning, we have multiple layers. They are matrix, so they can be replaced with tensor networks to compress information. The data size and parameter size can be reduced. As a result, you get a faster speed. So it's a recent idea that emerged. And we also have the PDE, partial differentiation equation. The field of flow or field of pressure can be replaced with 3D tensors. So similarly, you can use tensor network for compression. So context representation is utilized in different areas. So this is the way to express represent state. And then you can apply the partial differential equation. Now, this red font indicates our current project. There are two ways of quantum embedding. First, from quantum circuit to tensor network. This is easy. This is one-to-one relationship. So you can use conventional tensor networks to create high performance simulation, or by utilizing the NC sampling, you can have very Markov chain. You can actually improve the result of a simulation. Or quantum error correction. Tensor network decoders are known. Minimum weight perfect matching. Compared to that, we have better accuracy. But if you introduce noise model, we can predict much better. But we are developing in the process of quantum error correction, we would like to utilize syndrome representation to, without having additional quantum computation, we are trying to achieve higher accuracy or precision. Or in the lower part of the slide, you see it's not quantum circuit. When we have quantum state, is it possible to convert quantum state to a tensor network? It's almost like TN tomography. But this is very difficult. If this is possible, though, we can use that as a simulated quantum memory, or it could be used for long-distance communication. When you make the measurement, you have binary bit 0, 1, 0, 1, but rather than going down to 0, 1 conversion, the tensor network will be able to express the quantum state in approximate manner. We can just keep the state as is. The reverse process is to embed TN into quantum circuit. For example, this is one-dimensional loopless tensor network, NPS. There are multiple ways to embed that into quantum circuit, and this is quite successful. 3 tensor network, it's complex, but doesn't have any loops. We are developing methods to embed that efficiently when there is distribution in a state. Something like this. How can we convert that into the form of quantum circuit, possibly combining other measurement methods? That's one technique that we are considering. And there will be a presentation by Mr. Okubo this afternoon. So if you're interested, please come to that presentation. and tensor network quantum simulation. So we are thinking in this area is the real-time imaginary time evolution represented by tensor network, and then with that representation in use, we would like to conduct time evolution on a quantum computer. If this is possible, combining the technology that I explained one slide before, we will be able to embed that into quantum circuit, meaning that we will be able to connect quantum to quantum. So I'm repeating myself here, and this is what we want to achieve as we are promoting this project. SQAI, there is the exhibition booth. So if you are interested, please come visit our booth. Thank you for your listening.